SwayamPrabha. Digital India. Educated India.
In this lecture, let us look at results of some numerical simulations on shock diffraction, shock wave boundary layer interaction. We will make use of the open form CFD solver and do some studies on shock diffraction, hypersonic flow past a hollow flare and past a double ramp. Some of the related references which may be useful for you and which you can take note of in this context are given here. One of them happened to be a recent lecture in the HPC Research Week under the National Supercomputing Mission. The other few are some very recent publications from our group and which are connected with what we are going to discuss in this lecture. Let us start with shock diffraction and try to understand what it is, and we will gradually see that it is going to be a very widely occurring phenomena in compressible flows. Study of shock wave diffraction, shock-shock interaction and shock wave boundary layer interaction are essential for understanding internal, external compressible flows involving the interaction between shock wave and boundary layer over a solid surface, mitigating shock waves by designing effective shock resistant structures, mitigating shock induced separation bubble by designing efficient active and passive flow control techniques, understanding astrophysical flows with supernova remnants, cosmic shock collisions, etc. So, these are part of astrophysical flows and propagation of shock wave through microchannel in applications like lithotripsy. All these kind of applications that we are talking about definitely contain shock diffraction, shock interaction, shock wave boundary layer interaction, all these kind of phenomena. And shock wave diffraction is very rich in complex flow field features involving these kind of interactions, additionally shock vortex, shock turbulence, and therefore, it is worth looking at it. In this context, we will spend a minute telling you that in our research group we use open source CFD solvers, OpenFOAM, SU2, EcoGen, InCompact 3D, several of them for performing direct numerical simulations. That is, we do not use any modeling for capturing the turbulence, it is captured directly, and we definitely look at shock turbulence interaction in shock wave diffraction, shock boundary layer interaction, shock bubble interaction as well. We do not have time to elaborate on all possible problems that we look at, but it is important that from the course perspective we try to touch upon at least one or two of the important phenomena associated with shock interactions. We have chosen to discuss about shock diffraction. It is a very interesting phenomena. Additionally, a little bit on shock boundary layer interaction as well. You need a lot of computing resources for performing these very complex flow simulations. At IIT Kharagpur, we are privileged to have one of the best HPC setups, the Param Shakti supercomputer, which is located at our campus. In the numerical simulations that we have included here in the slides, we have used 8 high memory compute nodes of this HPC, in which we have utilized 16 GB RAM in each core. By utilizing this setup, our DNS took 6 hours on an average to complete. So, this is a small snapshot of the physical facility. You will find more details on it in this link. This is a kind of cartoon representing the broad layout of the HPC. Some more details: it has 2 master nodes, 8 login nodes, 10 service and management nodes, and 442 nodes comprising of CPUs and GPUs, giving a peak computing capacity of about 1.66 petaflops performance. It is based on Intel Xeon processors, NVIDIA Tesla V100 with, as I said earlier, peak performance of about 1.6 petaflops. It is having InfiniBand interconnect, and it is based on Lustre parallel file system. A little bit about the HPC facilities, and then we move on. As far as shock diffraction problem is concerned, we give some details about the solver schemes that we have used. We have used the row central foam solver in open foam for performing this exercise. The different schemes that have been used, where some improvisations also have been made by the research team that we have. The last one in particular, implementation of a semi-implicit Crank-Nicolson method for time stepping the solution. Apart from that, the spatial derivatives, the different types, the convective, viscous, the gradients are captured by the different discretization schemes that have been mentioned over here. Plus, since we are handling shocks around which oscillations occur in the solution due to Gibbs phenomena, are clipped using Van Leer limiter. With some details of the numerical schemes, we move on to say that the first problem that we would like to look at is the shock vortex interaction over a wedge during shock wave diffraction. This is the computational domain where you see the a broad view of the computational grid or mesh that has been deployed. And as you can understand that we have taken half of the wedge, basically we have not taken the full, and kind of applied the symmetry condition about this boundary. The flow comes in through this direction, leaves this way, and by halving the domain we save on computational cost. And it has been performed on an equilateral triangle wedge. Only flow over upper half has been calculated, and the side length is of the wedge is 20 millimeters. There is a shock coming in from this direction and impinging on this wedge, and then as it reaches the trailing edge of the wedge, then what you see forming is something like this, which has been elaborated in the third bullet point. So, the flow is approaching with the Mach number 1.38. So, it is basically a moving normal shock which is approaching the wedge. The static pressure of the free stream is mentioned here along with the temperature. The time at which the incident shock meets the leading edge of the wedge, that means basically this point is 40 microseconds from the start of the flow simulations. When the normal incident shock after colliding with the wedge travels downstream, a single Mach reflection occurs, causing a reflected shock R, that is this, an incident shock which moves on I, and a Mach stem that you see over here. It is very interesting flow field that is unfolding. Beyond the corner, the Mach stem diffracts and an expansion fan is generated in a pair with the diffracted Mach stem. A lambda shock appears along the emanating shear layer. The slip layer that coils at the corner of the wedge causes the formation of a vortex. So, some of these are not easy to understand from this view. Here the view has been shown when the total shock structure has just touched the trailing corner of the wedge, and then the diffraction phenomena basically will start beyond this time, and all the flow features that have been mentioned towards the end of this last bullet point would then surface, the details of which are available in this paper, which you can have a look at. And before we could go ahead simulating it all and be very confident that we are doing it fairly accurately, you need always to answer the question that whether the solver has been well validated or not. So, for the validation purpose, we took up results from another paper where the shadow graph of the flow at 128 microsecond from beginning of the flow was reported by the authors, while we did some kind of a numerical shadow graph by taking the Laplacian of the density and then trying to see it at about 128 microsecond from beginning of the flow, and we could see a fairly good match between what we see in the experiment reported in the paper and what we see in the numerical result that our solver generated. Again, details are found in this paper which you can have a look at. And then for the shock vortex problem, the shock diffraction problem, we then looked at tangential velocity distribution of primary vortex for x equal to 6 millimeter at 180 microsecond from beginning of the flow. There is a particular distribution that we validated with this particular paper. So, what we are talking about is basically that when the flow reaches this corner, then ultimately, apart from a lambda shock that forms somewhere here, there is also going to be a vortex formation, and at 180 microsecond, how the velocity distribution in the primary vortex is showing up is compared between what is reported by the paper above and the numerical results of the present study have been shown for 3 different grids again, because we need to make sure that we are using the correct grid which is matching well with an experimental data. So, that is what we call as grid convergence study, which is needed in any kind of CFD exercise. We also need to check the so called power spectrum density distribution of non-dimensional turbulent kinetic energy with respect to the Strouhal number, or essentially the frequency. To show how far the energy spectrum has been resolved. That is essential to make sure that the wide range of length and time scales which show up in such a complex flow field is well captured. This distribution follows the minus 5/3 log law, which is widely used and well known, which is sufficient to capture the highly anisotropic large scales which occur in this region, inertial subrange scales and a small portion. So, subranges occur somewhere here, and the small portion of viscous dissipation scales which occur at the higher frequencies. And the power spectrum, by virtue of its broad band, essentially establishes the fact that the wide range of length and time scales have been well captured, which is required in a typical DNS. Having said that, we move on to see how the flow really evolves, and you see interesting features over here at different times unfolding as the flow moves on. And the Reynolds number of the problem based on wedge length, shock speed and thermodynamic quantity like pressure, density or temperature shows up in this range. Contours of the density gradient magnitude are used effectively. So, that is what you see over here in both these plots. To elucidate the time evolution of the overall flow features, you see different features marked in the figures: the expansion waves, lambda shock, Mach stem, reflected Mach stem, formation of the primary vortex and so on. A slip line emanates from the triple point at 80 microsecond. The Mach stem reflects back from the center line of the wedge. So, the Mach stem went all the way up to the center line up to which we are computing, and then it reflects back because there is a Mach stem coming from the other corner of the wedge at the bottom, and they meet each other and they reflect back. So, this is basically the reflected portion of the Mach stem that we are talking about. and then the reflected Mach stem interacts with the primary vortex formed by the slip layer at about 100 microseconds. That's what you see over here. So, the reflected Mach stem goes and kind of meets the primary vortex. The induced flow velocity on the left side of the eye of the primary vortex has the same direction as that of the motion of the reflected Mach stem. Because the reflected Mach stem was moving up like this, the primary vortex, this part is moving down while this part is moving up. So, here the effects sum up while here they get kind of negated, and due to this there is some kind of accelerated shock wave and deaccelerated shock wave formation that we talk about over here in the last point, which we have mentioned over here. You see further that Kh instabilities, that means Kelvin Helmholtz instabilities, form in the shear layer, and you also can see the secondary vortices which are forming gradually on the wall, the base wall. So, this is basically the base of the wedge. So, it is forming at the corner of the base of the wedge. You also see weaker waves compared to the shocks which we are identifying as the acoustic waves. So, it is a very rich flow field with a lot of flow structures from which you can learn. And then if you look at contours of z component of vorticity, so that is basically omega z, then you see structures like this. Again, as we said earlier, that there is some kind of a separation, flow separation occurring at the corner of the base region of the wedge. When it comes to shock turbulence interaction, we found that there is a vector which we call as the Lamb vector, which is basically the cross product of the omega and u terms. If you take a divergence of that Lamb vector, it shows up in a form like this at about 80 microseconds. You see positive and negative values of the Lamb vector divergence juxtaposed next to each other if you look very carefully into this region. Blue and red bands, that is what it indicates. Positive value of divergence of the Lamb vector corresponds to fluid straining motion, and negative value represents vorticity bearing motion. You can expand the divergence L expression and show it to be of this form. So, if divergence of L is less than 0, then the term omega square is greater than u dot curl of omega, which represents vortical motions with depleted energy, while if divergence of L is greater than 0, then omega square is less than u dot curl of omega, which represents straining motion with high local energy concentration. Now, the region where a strong positive value of divergence of L is accompanied by a strong negative value, it leads to enhancement of momentum exchange due to high energy difference, causing amplification of turbulent kinetic energy, and therefore, divergence of Lamb vector happens to be a very important tool in understanding the turbulence interactions during the shock wave propagation. These are snapshots of how the Reynolds stresses behave. So, you may be aware that these terms are called as the Reynolds stresses. The double dashes are basically fluctuations of velocity components along the respective directions. So, this is basically a normal component, so is this along y and x respectively, while this is a shear component, and they are shown at about 100 to 120 microseconds from start of the flow, where the reddish patches indicate a very strong presence of these stresses. If you were to look at shock diffraction across a right angle step corner, then you would see something like this, which is also extremely interesting to watch. Here the mesh looks somewhat different. A very fine computational grid is of course necessary to resolve the flow features which are complex and diverse in nature in a flow field like this. You can see that because of the extremely high quality mesh, you see the finest details revealed in different portions of the flow field, where waves of varying strengths are advecting through the flow field, and some of the major features are marked on the figure itself. It is basically a numerical Schlieren which reveals important features of the flow: the lambda shock, KH instabilities, primary vortex, the contact surface which is indicated as CS, the vortex induced shocks. That means from the vortices shocks can be induced, which originates from the primary vortex and impinges on the base of the step. It interacts with the primary vortex and diverging acoustic waves. So, all kinds of intricate features are evident from the picture that you can see over here. This is another interesting picture, and the previous slide as well as this slide contains some of the results in this paper of ours, which has been published this year in 2024. And you see temperature fluctuation amplification indicated, where of course, if you are in the reddish part, those are the places where temperature fluctuations can be very, very intense. And this also gives you some idea that in these kind of flow fields there are significant thermal impacts as well. Now, let us move on to the next problem. So, we did some survey of the shock diffraction problem through a diffraction occurring across the rear corner of a wedge and of a square corner. Next problem we look at is numerical studies of shockwave boundary layer interaction over a hollow cylinder flare at thermochemical non-equilibrium hypervelocity flow. So, the flare is a structure like this that you see over here. It is a small hollow cylinder flare that it is showing in this figure. So, the flow basically approaches from the left towards the right of this body, and here we have used the Hy2Foam solver in OpenFOAM platform for performing this analysis, and we have tried to look at the different features of the flow and also explore the local surface heat transfer rate. Not all of this has been included in our slides here for the study, but the study that is reported in this paper of ours does include the details. The preliminary study of mass fraction of some of the species in the chemically reacting air mixtures has also been performed. So, we will try to see some of these results. So, the flow simulation details are given over here along with the numerical grid that has been used. As you can see that a lot of refinement of the grid is required to capture the near wall structures very effectively. The Navier-Stokes Fourier equations are solved with 11 species because it is a reacting flow. We will see soon based on the initial and boundary conditions. The different species are mentioned, and there are 20 chemical equations which are considered. So, it is a 20 equation model. The different discretization schemes that we also discussed for the shock diffraction problem are indicated in the next few bullet points, and then the vibrational translational energy transfer is taken care of by the Landau-Teller equation, chemistry and molecular vibration through Parkes 2 temperature model. These are the relevant details for the problem. The free stream conditions indicate that you have a fairly high enthalpy flow approaching at about Mach 12, and the free stream pressure, density, velocity, temperature, Reynolds number are all mentioned. The mass fractions of molecular nitrogen and oxygen are also included. The two important papers in this connection, of course, our paper which is indicated at the bottom, and another which has been referred for the work is mentioned on top as one. So, that is also mentioned here in the points that we have written for boundary conditions. Free stream boundary conditions are imposed at the inlet of the domain. Wave transmissive supersonic pressure outlet conditions are used at the outlet. The wave transmissive model prevents the reflection of compression and expansion and shock waves into the computational domain from the boundary. Isothermal no slip wall boundary condition is applied at the solid wall, maintaining it at 300 Kelvin, and it corresponds to the run 3 of the MacLean's paper, which is indicated here. The free stream is assumed to be at thermal equilibrium as mentioned in the experimental conditions. So, based on this, we continue with the chemical reactions that have been considered. We have the different categories. The first category being dissociation, where you see molecular oxygen and nitrogen colliding with a third body to dissociate. So does NO into its respective atoms. Then you have electron impact dissociation of N2, followed by exchange reactions between NO and O, N2 and O, electron impact ionization, where N or O impacts with electrons to ionize, associative ionization, where N or O collides with NO or O, and O plus with N2, where ionization is produced. Charge exchange happens for the remaining equations here, where number of species are involved, which you can go through one by one and check. And as far as these equations are concerned, you can go back to lecture 50 for more details on the chemical reactions in terms of Arrhenius constant, temperature of activation, temperature exponent, and so on. A very important reference in this connection is the paper by Park as well as his book. Looking at some of the results of this problem, we have three pictures basically over here. If we number them as 1, 2, 3, the first one indicates the separation bubble produced by the shock wave boundary layer interaction. So, you see the flow approaching towards the flare from the left, and then because of the viscous interaction, the shock interacts with the boundary layer, causing it to separate due to the adverse pressure gradient. You have the separation point here, the reattachment point here, and you have the separation bubble in between. So, the first picture talks about that. The second picture talks about translational and rotational energy mode temperature. The third one talks about vibrational and electronic energy mode temperature, and of course, we are referring to a 2 temperature model of Park here. Few important points: the adverse pressure gradient creates strong interaction between shock wave and boundary layer, causing flow separation, and there is a bubble formed near the compression corner. The translational and rotational energy modes get significantly excited within the bubble. It shows up through the color codings here. In the upstream region, because of the short forelength of the flare, the viscous dissipation effect hasn't been significant. So, that is through the weaker temperatures that you see here. Downstream of the reattachment point, which is here, the modes are damped near to the cold wall, but excited in the viscous dissipation region, that is this of the boundary layer further downstream. For the vibrational mode, which is basically the third picture, which is applicable again for only 6 molecular species out of the total 11 that have been taken, no significant mode excitation is observed up to the separation bubble. The intense heating in the shear layer reattachment zone increases the vibrational temperature and leads to energy mode excitation. So, most of it happens here. So, these are some of the findings. Coming to the mass fraction of species, you see that post reattachment changes in the mass fractions of N2 O2. So, you see a dip in O2 mass fraction, a much milder dip in N2, because that is expected to start at yet higher temperature. Correspondingly, increase in normalized mass fractions of NO plus and O plus at the reattachment zone. Both NO plus and O plus form at the post reattachment zone of the separated shear layer. Decomposition of N2 and O2, NO formation and its ionization, O formation and its ionization are all intermediate reactions that lead to formation of the above species, and the mass fraction variations, both growth and delay, are confined to the post reattachment zone. So, these are some of the things that you can conclude from that study. Moving to the last slide of this lecture effectively. So, this is a slide on a double ramp or a double wedge as mentioned here, and there is this is basically indicating the shocks, different kinds of shocks that have occurred over here. It is a very complex interaction. Those shocks are basically identified from a numerical Schlieren, where you try to carry out the gradient of density and take its magnitude, and then the contours are basically coming from the turbulent kinetic energy. The turbulent kinetic energy, which is represented by the K here, and it shows you different kinds of color patches which indicates different levels of turbulence which has been generated. An important thing to note over here is that if it was an inviscid flow, you might have expected something like this happening here. So, a hypersonic flow approaching the double wedge, creating the first oblique shock here, followed by the second oblique shock with the deflections, if you call them as theta 1 and theta 2 respectively. If they at this given Mach number provided attached straight oblique shocks, then they would actually look like this, where the shock propagates from the wall. While always keep in mind that in the case of a viscous simulation, the shocks would never reach the wall. They can at most percolate up to the sonic line. And additionally, because of the effect of the adverse pressure gradient produced by the shocks, the boundary layers tend to separate, and this is essentially footprint of a separation bubble which is forming over there. There are also some unsteady effects which we are not going into, but this kind of a configuration, this kind of a geometry is widely used in supersonic, hypersonic intakes for slowing down the high velocity inflow to lower velocities before the flow can be injected and burnt in the flow to generate thrust. So, it has to do a lot with high speed vehicle engines. So, you may be thinking about the ramjets and scramjets, and you are rightly thinking so. With this, let us conclude. In this lecture, we discussed about CFD simulations results using the open form CFD solver. We discussed about shock diffraction across a triangular wedge corner and a right angle step corner. We discussed about hypersonic flow past a hollow flare, and we started discussing about hypersonic flow past a double ram. Perhaps we will discuss a little bit more in the next lecture. Thank you.